Okay, guys, so we'll get through as much of the Unit 7 as we can today. A lot of the process we go through, you know, the conclusion, checking conditions, a lot of that stuff is very similar to what we've been doing with hypothesis testing, so that shouldn't be too overwhelming. All right, guys, we are talking about the chi-square distribution this unit. So first, we'll talk about the shape a little bit. It's always going to be skewed to the right like that. Skew right. As degrees of freedom increase, the shape becomes more normal. And we will always use this with categorical data. And it's always going to be a one-tailed type of test, okay? So you're always going to have your little picture drawn, and you'll be shading somewhere over here.
What is the second?
As degrees of freedom increase, that's a little DF there. Yeah, sorry. So degrees of freedom aren't solely based on n. They're going to be based on rows and columns of a matrix this time. So it's not bad. I promise. You have to do like 4 minus 1 times 3 minus 1 to get your degrees of freedom. You can do that.
Oh, I don't know.
Promise it's not bad. All right, there's 3 different types of tests we can do with the chi-square distribution. We have the goodness of fit test. That's the first one. Again, we're always working with categorical variables when we're doing chi-square. The goodness of fit is often abbreviated GOF. You still have to write a null and an alternative. And most of these are going to be stated in words this time instead of like, you know, before we do like mu equals something. Here, because there's so many different pieces you're looking at, it's easier to write it in words than it is to write out all the different pieces. All right, your conditions. And stop me if I go too fast through anything or you have questions, okay? So the first one, you know, normally we would check normality. This one's a little different for the chi-square test. What you're going to look for is the expected counts. So we need all expected counts to be greater than or equal to 5. And I know you're going, well, what's an expected count? That's okay. When we get to the example, you'll see how all of this works. But that's the first condition you check. All right, we're going to check for a random sample again. And then the independence 10% rule, again, we won't check for now, but be aware of it. So for this first goodness of fit test, you're just going to do the expected counts greater than or equal to 5 and that it's a random sample. Okay. That independence 10% rule will definitely pop up on the Khan Academy questions. We won't check now. I know that's weird. Let's try a different. See if this right thing better for us. All right, so our test statistic, before we would have a z or a t was equal to something. Now you're going to have a chi-squared is equal to something. You have this formula. It's a pretty simple formula. Do you guys know what the lovely looking weird E does? It's summation. Okay, so this is the sum of all of the observed values minus the expected values squared over the expected value. So if you actually wrote it out, you'd have, you know, sum observed minus an expected squared over an expected plus a different observed minus a different expected squared. Okay? We're not going to do this by hand. Your calculator will do it for you. Yeah. Yep, just this. No, use the sigma. Yeah. That's just what it means it would be doing, but we don't have to actually do it that way. And again, the O is the observed count, meaning like what you actually saw when you collected the data, and the E is the expected count based on whatever you think is happening in this situation. All right, with goodness of fit, degrees of freedom is still pretty simple here. It's just k minus 1, and k now is our number of categories. So we don't have a sample size in the same way that we did before. We're dealing with categorical data instead of quantitative, so it looks a little different. But your degrees of freedom is just however many categories you have minus 1. And so for this test, we'll be using lists on your calculator, okay? We'll get into matrices for some of them, but this first one, the goodness of fit, is just using lists. Why is it always minus 1? So it's not always minus 1. For everything we've been doing so far, you do a subtraction of 1. It's just the formula you have to follow. There's a very complicated reason that it's not going to help you at this point, okay? You just need to know, I do categories minus 1. Okay, fine.
What is this?
Don't worry about this one right now, okay? It's multiplying the, like, you're going to have a proportion like 10%, 20%, 30%. You take that times the sample size for however many things you collected, but we'll get into it with an example, okay? Okay, let's try one so you guys can see what all of these pieces are talking about. So we've got a company here. They collected some data on the distribution of when customers arrive, what date. So they randomly chose a week, and then they counted the number of customers each day. So on Monday, 31 customers came, Tuesday was 18, Wednesday 36, Thursday 23, Friday 47, Saturday 60. And that's the sample information we have. And we are going to test to see if these expected amount of customers is actually what happens, okay? So let's walk through all the pieces of this. So first, I'm going to kind of make a grid along here so that I can see everything. Hopefully your lines are straighter than mine. So first thing we're going to do is write in the percentages. So it's 10%. I'm going to write 0.1 next to it. I know you know what these are, but we're just going to write them just to make sure we don't mess it up. And you don't need to write 100%. That's just the total at the end. And then I'm going to make a couple of lists over here. These are the lists that would go in my calculator. So list 1 is going to be our observed. So this is what we actually collected when we chose the random week to watch customers and when they came. So guys, observed, how many people actually came on Monday?
31.
31. Yeah, what we put in this, the observed, is the actual data of who came when. So on Monday we had 31 people. What about on Tuesday? 18. On Wednesday, 36. On Thursday, 23. Friday, I have a really small spot for 47. And then Saturday was 60. So guys, we need to also know the total number of customers who came. So add that up for me. And guys, definitely have your calculators out. We will be using them to actually do our hypothesis test here. 215, guys. So we had 215 total customers. That's what we observed. We now want to know, how does that compare with what we would have expected to happen? So that's what's going to go in our list 2, is expected counts, okay? Now I know I had 31 actually show up on Monday. How many do you think I expected to show up on Monday? 21.5. Yeah, you do that percent, the 10%, times the total number of people we were looking at. Like, we know we had this many come during the week. Here's how we think they would have come on which day. So that first one is 21.5. Do you guys see that Tuesday is going to be the same thing? All right, what about Wednesday? 32.25. And Thursday would be the same as that. All right, what about Friday? 43, good. And Saturday. Okay. And you don't have to add all of those up, okay? It should be the same. All right, everybody with me so far on how you get those two values, or all those values in those lists? Yeah. Yeah, you can just leave them as these decimals, but you could also do it rounded and you'd be okay. So it makes perfect sense that we aren't going to have a quarter of a person come on a certain day. So yes, I understand. 43, yes. Yeah. So we had the percentage, so like Monday, the expected percentage was 10%. So we took 10% times this total. Like, we know we had 250 people come. This is how many we would expect to come on each day. All right, so that's sort of just the breakdown of all of our data there. Now we're going to go ahead and do our test. So this is called the chi-squared goodness of fit test. Just want to label that somewhere. Here's what we're doing. Okay, and the first thing we're going to do is write out our null and our alternative hypothesis. So what I was saying before, that you're going to want to do it in words, it's easier than writing out like, our null is that 10% of the customers come on Monday and 10% of the customers come on Tuesday and 15%. Like, does anybody want to write all of that out? No, I do not want to write all that out. So what we can do instead, we can say the company's customer projections are correct. So what they expected to happen is correct. That's our null. What do you think the alternative is going to be? They are not correct. And we're going to say for at least one day. Okay? It's not that every day has to be wrong, but at least one day would be wrong. No, we're just saying, like, that's saying they're all correct. Yep. Anything else with the null and alternative? All right, conditions. All right, the first one that was a little different, we are looking at the expected counts. So go back up here and look at your list of expected counts. Are they all at least 5? Yeah, so that's what we say. All expected counts are greater than or equal to 5.
For that, were you using the percentage or the number?
The actual count. So this right here, this expected list, these are the counts of people. And then our next one is simple random sample. What do you think? Was it a simple random sample? Yeah, and it was stated, right? They said they randomly picked a week, so we'll go with that. Stated. Okay. That's happier than conditions for like the 2 sample hypothesis testing, right? Easier. All right, so let's go through what we would actually do on our calculator here. We'll write down our formula and then we'll look at how we key it all in. So our chi-squared formula is just the summation of observed minus expected squared over expected. And then go ahead and get out your calculator.
Is it like a standard year or something different? I should.
What do you mean?
Is the E stand for a symbol or is it?
Oh, it's expected. Yes. Sorry, I was like
I know it.
the O and the E. And you could write, if you're like, I don't like that, you could certainly write like observed minus expected squared. Like, that's fine. All right, let me get my calculator over here. Okay, we're using lists this time, right? Where do I go to put lists in? Okay. Or you can just go right to stat and then edit it. Okay. So in list one, I want to put the observed. So that was 31, 18, 36, 23, 47, 60. And then list two, we put our expected. So 21.5, 32.25. Hello. All right, once you have your lists in, we're going to go to stat again, and then arrow over to tests.
Is there a way that you can like clear like a number? I accidentally want to accident.
Yeah. Don't delete when you're talking to this, because I mean, higher list.
What do you clear?
Where's oh, sorry. Okay, and we're going to start scrolling until we see something that looks promising. Oh, okay, we've got two of them with chi-square, right? If you pick the wrong one, if you're like, oh, I'm doing a chi-square test, you'll get here. This is asking you for matrix A and matrix B. Have we done anything with matrices yet? Nope, so that's probably not the test you want to pick. We are doing the goodness of fit test, so we want to pick that one. And it even helps you out with like, okay, yes, we want your observed and your expected. Okay, now degrees of freedom. What is it? How do I find that? Yes. So how many days did we look at? 6. So 5 is correct for my degrees of freedom. Okay. Thank you. And then let's go ahead. I'm going to pick draw again because that reminds me that I need to make a picture. All right. If you are not getting that lovely picture, raise your hand. Let me come help you. Okay. So in your y equals with that.
Oh, okay.
You know, it's
Not
we
sure.
want. Yeah, I always have like buttons we push to the right. Ooh, so good. I just turned one of your scaffold off. It was trying to like grab the three.
Okay.
Miguel? Okay. All right, guys, so this gives you everything you need to finish out your test. You've got your chi-square value, you've got your p-value, your picture that you can copy. You got to get all of this back on your paper. So the chi-square value was, I think it was it 8.54? Something like that. What if it's not shaded? Yours, what does your p-value say? Yeah, that's not right. Mine's 0.1.
What is happening?
You had a 36 instead of a 31.
I just have dead eyes.
We're all there now. Guys, a couple other things you want to list. We want to list our degrees of freedom. Just tell me, hey, I did 6 minus 1, which is 5. And then I'm going to make the sketch and also list the p-value over here. Is it 0.128 something, 89 maybe? So guys, what you label on your sketch, this is always 0. And then it's your chi-square value that you are labeling here. And then we shade. And now we're back to stuff we know. We have a p-value and we have to write a conclusion. So are we rejecting or failing to reject? Yes, since our p-value. Uh, 0.1289 is greater than alpha of 0.05, which I think they gave us in the problem. Yeah. We failed to reject the null. There is not enough evidence to suggest that the company's projections are not correct. So the end of this, very familiar, right? Nothing new there. Question. That was a heavy sigh. All right, we've made it through one text, guys. Turn the page when you're ready. Stay here for a second. All right, guys. Okay, so our next one is the test for independence. This is still a chi-square test. It's just a different type of chi-square test. With this one, you normally have two categorical variables. And then we've got to write a null and an alternative. The null is always something like the variables are not associated. Like, that's what we're testing is independence or association. So two ways you could write it. The variables or you could say they are independent. Okay. You don't have to say both. You just pick which way you're going to phrase it. And then the alternative is that the variables are associated. Or if you're writing it with the word independent, you could say they are not independent. And obviously you have to put context in with your null and alternative. We don't just say the variables. We talk about whatever it is we're talking about. What do you think the first condition is going to be here? Yeah, the same as the other one. All expected counts are greater than or equal to 5. And then we still have random sample. Now, I didn't even list the independent condition here. Why do you think I didn't list it? Well, yeah, that's what we're testing, right? So we can't be like, oh, they're independent in our conditions and then do a test for independence. That would not make much sense. So we don't mention independence when we're doing this type of test. And then your test statistic, all of this stuff is the same as it was for the first chi-square. So you've got your chi-squared equals the sum of observed minus expected squared over expected. Again, the E is the expected count. Now, degrees of freedom looks different. R minus 1 times C minus 1. That is just row, however many rows you have minus 1 times columns minus 1. Mhm. So if you're doing the test for independence, you're going to have rows and columns and a matrix, and this is how you'll calculate degrees of freedom. If it's the first one that we just did, the goodness of fit, then you just do categories minus 1. Okay? All right. So again, when we're doing this type of test, you're going to use matrices. Okay? So it's a different type than what we did for goodness of fit. Goodness of fit uses lists. The other chi-square tests use matrices. And I will show you how to use a matrix on your calculator, okay? All right, so turn the page when you're ready. Okay, so we're looking at the relationship between the grade earned in English and the number of hours per week that a student reads. So this survey of 500 students gave us this frequency distribution. So we've got less than 2 hours, between 2 and 4 hours, or more than 4 hours. And then the grades A, B, C, D, and F. Okay? So how many rows do I have? How many rows do okay, good. 3 rows. And then these are your columns, guys. How many columns? 5 columns, okay. Draw some lines here. So over here on the right, these are your row totals. Along the bottom, these are your column totals, which I know this seems like common sense, but we're just going to label it. And you might hear me reference what was the total. That's the 500, okay? That's this guy, so that's total. All right, we're going to actually do our hypothesis test. And again, this is the chi-squared test of independence. So state that somewhere at the top. That's what we're doing. All right, and then again, our null and alternative, we're writing in words, okay? I'm going to write it with the word independent in there. Again, you could do it with association. It's just slightly different wording. So I'm going to say number of hours reading per week and grades are independent. So the null is always to start out that they are independent. What that means is that there's no connection between these 2 categorical variables that we're talking about, hours spent reading and grade in English class, okay? So that's the null. The alternative is that the number of hours of reading per week and grades are not independent. It's okay. It doesn't feel alone now. All right, are we okay with the null and alternative? So just put your context in there, but otherwise you say the same thing every time. Say not independent, I know. All right, so up next would be our conditions. And our first condition is that all expected counts are greater than or equal to 5. Well, have we figured out anything with our expected counts? No, we have our observed. That's the data we have. We need to figure out the expected. Now, you could do it by hand. You could figure out the percentage we would see in each of these grades with each level of reading and do it all by hand. I would not recommend that. Your calculator will do all of these for you. So, get out your calculator again. Okay, we need to go into our matrices. I almost said we need to go into the matrix, and that just feels like a lot today. So second, and then this little x to the negative 1. Do you see it in blue on the left there where it says matrix? That's where we're trying to go.
Wait, how do you get there?
Second, and then matrix is written in blue on the left. Do you see it? Anybody not finding it? So look on the go left column all the way down. It's the fourth button down. You see in blue above it, it says matrix.
Oh, yeah.
Okay, so second and then that button. Okay. We've got the names of our matrices, which are lovely. We can apparently do math with our matrices. You used to use this all the time, like in Algebra 2, and it's just not taught anymore. So we're going to edit a matrix. We're going to edit matrix A.
What is a matrix?
So it's like, if you write it on paper, you would do like this, and you'd be like 3, 2, 7, 5, 1, 8, 2, 4, 9. And this is a 3 by 3 matrix.
Oh.
So you can use it when you're solving systems of equations. Like, do you remember solving where you do like substitution or elimination?
Yeah.
If you have a system that has 3 equations and 3 unknowns, that's really tedious to do with one of those methods, but you can do it with a matrix really quickly. So I don't know why they don't.
Does it just like multiply all the numbers or something?
Kind of. It does different things. Like you can find the determinant, you can make an augmented matrix, you can do all this different stuff. There's a whole course on matrix algebra, so yeah. We're just gonna edit a matrix. So yeah.
When you say like a 3 by 3, is that the row first or
Yes,
column?
it's always rows by column. Yep. All right, guys, we are going to fill in matrix A. So we do not have a 1 by 1 matrix. If you look at our hours reading and grades, what do you think our matrix is? A what by what? A 3 by 5. Yes, it's always rows first and then columns. So 3 by 5. And now, guys, if you mess it up and you type in 5 by 3, you would see very quickly that that's not the same setup, and then you go fix it, okay? So if you forget, just try, and you'll figure it out. So now I have to type in all of these values that I got. So, like, the first spot there's going to be the 36, okay? You see all the counts we've got from the different grades? We're putting all of this. 811, that's probably not going to work. All right, everybody have their counts in there? Okay. I know we haven't checked the conditions yet. We're actually going to do the chi-square test so that we can get the expected values from our calculator without having to do that by hand. So go into stat. I'm going to go over to test. Now this time, I'm not doing a goodness of fit test. Okay, remember that's the one that has lists. That's not what we're doing. We're just doing the chi-square test. So pick letter C. Okay, I put all of my observed values in matrix A.
Sorry. Just missed that, okay.
You're like, how did that happen? Where are you? Stat. Because you did all your values in your matrix, right?
Yeah, I got it.
Okay. Over to test. It's okay. It is, guys. We're going to make it through this week. We are. Promise. I think. All right. We don't want goodness of fit this time. We want the other chi-square. Just the regular chi-square. Okay. Observe, we put an A. I know it says expected in matrix B, and we did not put anything in matrix B. That's okay. It's going to calculate those expected values for you and put them in matrix B for you. That's when you say, thank you, calculator. And again, I'm going to go ahead and draw so that I can see what it looks like. Let me know if you are not getting the same numbers as me. Or just in general, if things are not going well, let me know. You what? Just think, the more we get done today, the less we have to do on Thursday, okay? All right, is everybody okay with this chi-square value and this p-value, all of that stuff? Okay, so keep it on your calculator. We aren't going to use it just yet. You do need to look at what those expected counts were. The calculator clearly did something. We don't know what they are yet. So I'm going to go back to matrix. So second matrix. Do you see now? It's like, oh, there is a B matrix, another 3 by 5. Okay, that's good. I would arrow over to edit so you can see it. Just push enter. Ooh, I did not see it. Why does it want to keep going there? Hold on. I want to save this matrix. Okay. You can go to edit, or if you just go to names and click B, then it'll pull up the whole matrix for you. Are you guys seeing this? Oh my goodness. No, I'm teasing. Okay, go back into matrix.
Oh, yes.
And then names, I'm just going to go down to B. You could also do it from edit and just look at them there. But you could like type something and mess it all up. So sometimes just seeing it from here. Now if I have a lovely B, that doesn't really tell me much, but if I push enter again, then it gives me all of the values.
The decimals make it a lot to look at.
It is a lot to look at. Are we very happy that we didn't calculate all of those by hand? You have to figure out like each percentage that would be expected based on all the different column totals, row totals, and total. That's hard to say. So again, you don't really want to do that by hand. One year I did make them do it by hand, my whole class, and it was very painful. We don't need to do it. How did I get here? Okay. So home screen blank, yes? Okay. Second, matrix. Yes, arrow down to B, enter, and then enter. Yeah, okay. No, you're fine. I want to make sure everybody sees it. Yes, you're going to have to scroll to be able to see all of your numbers, and I know it's a lot to look at with all of the decimals, and it's easy to get kind of lost in what's happening there. It's probably easier on your calculator than up here online. So, what we have to do with that, this part is a little less fun. We have to actually write out our expected counts. So I'm going to make a little table. You could put it up there, absolutely. That is fine. I wonder, will mine fit? I can fit mine in there, yeah.
Wait, we could write the numbers just like next to the.
Yes, let's do that. So go in your table. I'll do mine in like a different color. I'll make it easy. So I'm just going to jot down the expected counts, and I'm just going to go to one decimal place. So 50.4, because we don't really need these. You could even just round to the nearest whole number, because none of them are, what do we care about? Like, why am I even doing this? Well, we're going to do the independent part in a little bit. What do I look at with these numbers? Like, why do I care about them at all? Yes, they all have to be greater than or equal to 5, okay? So they're not close, right? So that's why I'm saying it's okay if you round. If you had one that was like 4.6 and you rounded it up to 5, that would be something to pay attention to. But none of these are close. And I don't know if you can read these. They're really smushed in there, but you've got them on your calculator too. Now, if you didn't do it on your calculator, then find a friend. I don't know why I wrote that. It is 26.6. I'm just testing you. Good job. You're paying attention. I mean, I guess this last one is close. 5.3. Okay. With the arrow.
It doesn't work.
It doesn't work on here?
It's easier to look at it. Yeah, I agree.
This one's easy.
Oh, wait. Still too late though.
Wait, what?
It's too late into the calculator.
December 14th.
It's too close to Christmas.
And then we come back from break and you're going to go, no, it's too close to break having just ended. We can't do anything.
We need like a buffer week on both sides.
Yeah. This is the buffer week.
The week after 4.
Yeah.
I think that week is hard.
I think the first full week that usually happens in February is good. Because like you haven't been in school.
January is just gonna, there's gonna be no rhythm to January. It's just gonna be. No, just show them somewhere. So you can write them in the table, you can make your own little table, just like show that, hey, I actually looked at the expected counts. I'm not just saying, oh yes, they're all bigger than 5. Like, you're showing that you did something. Well, then I might write on your test, where are your counts? All right, guys, what's our other condition we need? Random. Was it random, or do we have to assume? Yeah, it just says a survey, so we're going to do SRS, assumed. All right, so now look back at your calculator for the actual test that you did. If you need to run it again, that's fine. I'm going to make the sketch. We'll write out our formula here. We know it's the summation of observed minus expected squared over expected. That formula is actually easy to remember, unlike so many of your other formulas. Yes. I think we got 34.35. Now, degrees of freedom. I know you didn't have to put it in your calculator, but what are they? How do I find them? 8, yes. Oh, did it? Wonderful. Row minus 1.
That is how
Columns minus 1. 8. Okay, we can do that. My calculator told me. All right, and then p-value, I'm going to say the p-value is 0. Some of you might have had a weird scientific notation way of writing it, but I think most of you have probably just said 0. When you look at the picture and nothing is shaded on it, that means your p-value is 0. So what does that mean? We reject, yes. I know, right? Yeah, they're associated. All right, since our p-value of 0 is less than alpha 0.05, we reject the null. There is enough evidence. To suggest. See ya. That hours spent reading and grades are not independent. Or you could have said, suggest that hours spent reading and grades are associated, like there's some sort of connection between the two. So, not likely you're going to run into it. You could honestly argue either way. You could tell me, well, I think this based on whatever it is, or you could think the other way. It's up to you at that point. I don't plan to give you one of those. Okay? All right, guys, questions on that one? Again, once we get to the end, we're getting pretty good at those, right? The conclusion where we can do those, yes. Okay. All right, guys, we have one more type of chi-square test. Yes, we do. We can do it, guys. Yes. No, because on Thursday, you guys are going to be like, oh, it's so close to break. Yeah. We're not doing it then. Doing it now. Yeah, you're right. All right, it is the chi-square test of homogeneity. All right, this, you have one categorical variable. With at least two possibilities and two or more populations. I know, that's a lot, isn't it? Nope, there's no two-tailed test. So your two possibilities would be like voting and not voting. And then your two populations could be different age groups or things like that. So is it the what? Nope. We will get to the tree stuff. That's all with probability. That's not this. No, this is still matrices for this one, okay? They do get sometimes. Big trees. All right, we're still gonna write a null and an alternative. So your general sort of wording, if it's this type of test, is the proportion of members of each population with this characteristic is the same. I bet you can guess the alternative. Proportion of members each population with this characteristic is not the same. All right, conditions. What do you think the first one is? Yes. All expected counts. Greater than or equal to 5. We'll talk about the samples being independent since we're looking at 2 different populations this time. The rest the same, still the same formula for chi-square, observed, expected count. Again, we're using matrices, so we've got the rows and columns for our degrees of freedom. All right, turn the page when you're ready. One more example, okay? We're almost there. Nothing like all of your Unit 7 notes in one day, guys. No. Why this is number 12, I don't know, but it is. All right, so we've got an election coming up. Senator Smirk and Governor Graft. So they took a simple random sample of potential voters in the southern and northern portions of the state and asked them if they've decided who they're voting for or still undecided. So we've got all of our information there. So guys, do you see how right away it's easy to tell that this is not a goodness of fit test? Like, are you seeing the difference between the goodness of fit and the 2 matrix ones? Like, clearly this is not a list of information, okay? So we know we're doing the matrix type of test. We want to know, is there convincing evidence, its difference, the distribution of voters who have decided and undecided in the 2 regions. So what we're looking at is it the same between the North and the South? The proportion of people who have decided on a candidate and the proportion that are still undecided. That's what the test for homogeneity is. Is it the same across these 2 groups, these 2 populations that we're looking at? All right, so let's write our null and our alternative. All right, so we're looking at the distribution. And I called it candidate decisions. You could call it something else. So the distribution of candidate decisions. Candidate spell candidate. Is the same. Among northern and southern voters. And then your alternative is that this distribution is not the same. Okay. All right, conditions. So first, the expected count's greater than or equal to 5. What do we have to do to find that?
The same thing.
Yeah, we're going to actually do the chi-square test and look at it. It's fewer numbers this time, guys. What kind of matrix do we have? What size? 2 by 2, yes. So I'm going to go over to edit. What? No, so when I go to edit, I'll change this to 2 by 2. And then you just type your new numbers in. So when you do the test, it will put it in B for you. Yes, you don't have to like do anything. It's not going to say these don't match. I know. With the chi-square stuff, your calculator is pretty helpful. Okay, so what do I do with it now? Step, test, C. Go down there to just the chi-square test. I am not in test. There we go. What's up? Oh, why does it look like that? I know, it's kind of weird. It's just because of the scale on there, and that's just the shape of it, so this is why it's nice. Have it draw it for you, and then you can just copy what it is. You would have been here, you would have been like, That's
We
okay.
use the same X squared test.
Chi-square test, yep. If you are not getting that chi-square or p-value, let me know. If you are, jot them down, guys. It's okay. All right, guys. Again, jot these down so you've got these values. Because now what do we need to go look at? What do I need to check? Yes, I got to go into matrix. And again, you can look at the names, or if you go over to edit, sometimes it's easier to see there. Clearly, those are all bigger than 5, right? I didn't write these down anywhere, so hold on. So again, you could put them up here if you wanted to in your original chart. So yes, all expected counts are greater than or equal to 5. What do we think about random? Yes, and we're going to say simple random sample of northern and southern regions was stated. It's what?
That's like so many more words than we need to do. Are we gonna have to do that for all of them? Like for all of the
Well, you've got 2 populations, so you could do SRS of northern stated, SRS of southern stated. You seem kind of complainy today. You have less than 10 minutes left. I think you can make it. All right, and we're going to assume independent samples. I don't think it said anything about them being independent, so we're going to assume that, okay? Then the rest is everything you already did on your calculator. You're going to write down the chi-squared formula and give me that value. Which I think was 2.9-ish, something like that, 2.93 maybe. What were my degrees of freedom? 1, right? Row minus 1, so 2 minus 1 times column minus 1 is 1. And draw the weird picture. It's different this time, so this was at 0. Kind of went this way. It doesn't matter if you sketch it that way or if you do this, it's fine. We were a little bit shaded over here at 2.9. P-value of 0.087. Are we gonna what? I'm sorry. I mean, it could be like a multiple choice question, just like, what are the degrees of freedom here? So. No, it's just something you always want to list and be aware of, yeah. Yeah, that's what I was saying. If you copy it like exactly the way it is and draw it this way, fine. If you're like, oh, I draw them like this, fine. I just want your sketch, some shading, and your chi-square value on it. Okay. All right, our conclusion, guys, our last piece. What are we doing? Fail to reject, yes. Since our p-value of 0.087 is greater than alpha of 0.05, We fail to reject the null. There is not enough evidence. To suggest that the distribution of candidate decisions is not the same northern and southern regions. You made it, guys! Woo! All right, questions on anything from Unit 7 so far? Clearly the hard part is going to be picking which test you're actually doing. Like, doing this is not that hard. Deciding what you're doing is where it's hard. So that's what we will practice lots of. Ethan? That's fine. Yep, absolutely. Like to look for? Yeah, so if you think about, yeah, you're looking for evidence, that sort of thing. So if you think about, if you look at the examples, thank you. The goodness of fit one, clearly, like that's the easy one. Yeah, so you're like, all right, I got list, this is goodness of fit. Okay. Hold on, let me stop recording real quick.